Hello, teacher engineers. This is our last example for beam deflection by double integration method. Compute deflection at B, slope just to the left, slope just to the right, and the deflection at D by the double integration method. Moment of inertia of portion ABCD is I, while for DEF it is 2I. E is constant. So first, take note that the beam is determinate and stable. So we have two support reactions here, 2 plus 1, 5, plus 2, 7, plus 1, 8, plus 1, 9. And there are three parts or three free body diagrams. Therefore, 9 is equal to 3 times n. And in each free body diagram, we have three equilibrium equations. So first, let's consider AB because the load is at the center. Therefore, its vertical reaction as at A and B will be half of 30, so 15 kilonewtons as shown in the figure. So by action-reaction, we transmit 15 kilonewtons to the right to B downward. Then next, we consider BCD to solve for the reaction at C. Let's assume that the reaction at C is upward. So summation moment about D equals 0 or MD equals 0, considering BCD. So clockwise positive. So we have R sub C times 4 plus 90. Then minus 15 times 7. Then minus 20 times 3. 1.5 plus 4 is 5.5. The moment arm is 5.5. So minus 20 times 3 times 5.5. So that's it. Solving for R sub C. R sub C is 86.25 kilonewtons as shown in the figure. Then for the reaction at D, just sum up forces Y for portion BCD equals 0. So negative 15 minus 20 times 3 plus 86.25, assuming vertical reaction at D is upward, so plus D sub V. Solving for D sub V. D sub V is equal to negative 11.25 kilonewtons. Since it is negative, therefore it should be downward. So downward at the left, upward at the right of D. So finally, for portion DEF, we assume reaction at D as upward, summation moment at F equals 0, clockwise positive, so R sub E times 6 plus 11.25 times 11, then minus 15 times 11, moment arm is 5.5 from F, half of 11, so minus 15 times 11 times 5.5. Solving for R sub E is 130.625 kilonewtons. So that's it. Then finally, for RF, it is not important anymore in our solution. But if you want to check, it is 23.125 kilonewtons. You may sum up moment about D or about E, or you just sum up forces vertical to show that it is 23.125 kilonewtons. Then check whole system if it is in equilibrium. So we now establish the differential equation of the elastic curve for portion AB. That's the sectioning, call that X. So therefore EI y double prime AB is equal to 15 times X minus 30 times quantity X minus 2. So integrating EI y prime AB is equal to 7.5 x squared minus 15x quantity x minus 2 quantity squared plus constant of integration c sub 1. Take note that there is no c sub 2 because when x is 0, YA or delta A is 0. Integrating EIY AB equals 2.5 x cubed 7.2 over 3 minus 5x minus 2 quantity cube plus C sub 1x. There's no C sub 2. So 15 over 3 is 5. That's why it is minus 5 quantity x minus 2 quantity cube. Then we can have established boundary equation for AB because there's no more support where the deflection is 0. So we proceed to BCD. Then we have our reference at B. So since B is the origin, we have constant C sub 3 and C sub 4. C sub 3 is the slope just to the right of B, while C sub 4 would be the deflection at B. So we extend the loading so that it is applicable up to this section here, and we counter it by an upward loading of 20 kilonewtons per meter. So EI Y double prime BD is equal to 86.25 times quantity x minus 3. This one, moment about this section here. Clockwise positive plus 90 times plus this loading, moment of this loading, which is 20 times quantity x minus 3 times x minus 3 over 2. So it is plus 10 x minus 3 square. Again, 20 times x minus 3, the length, x minus 3. Then moment arm x minus 3 over 2. So plus 10 quantity x minus 3 square. Then plus 90 times quantity x minus 5 to the 0. Because it is not acting at the origin, so we have this moment arm, so that when we have the boundary conditions or the application, if the quantity inside is negative, so it is not included in the calculations. Then minus 15 times x minus 20 times x over 2, or minus 10x squared. So that's the differential equation for portion BCD. Integrating EIY prime BD, 43.125 quantity x minus 3 square plus 10 over 3 quantity x minus 3 cube plus 90 quantity x minus 5 raised to 1, or x 190 times x minus 5 minus 7.5 x squared minus 10 thirds x cube plus C sub 3. Integrating further, 43.125 over 3 is 14.375 x minus 3 cube plus 10 over 3 times 4, so 10 over 12, or 5 over 6 x minus 3 to the 4th plus 90 over 2, so 45 quantity x minus 5 square, 7.5 over 3, so minus 2.5 x cube, 10 over 3 times 4, 10 over 12, so minus 5 6x to the 4th plus C sub 3x plus C sub 4. Remember, C sub 3 is the slope just to the right of B, and C sub 4 is the deflection at B. Although slope at B is not required, but just anticipate the interpretation of these constants. Then boundary condition, when x is 3, yc is 0, so into this equation here. So this first term is 0, the second term 0, third term is ignored, negative. So let's begin with negative 2.5 x cubed, so negative 2.5 3 cubed minus 5 6 of 3 to the 4th plus C sub 3 times 3 plus C sub 4. So the first equation is 3C sub 3 plus C sub 4 equals 2.5 times 3 cubed plus 5 6 3 to the 4th, that's 135. Call that equation 1. Then we establish differential equation for the remaining segment of the beam DEF. So let's have this sectioning applicable to all sections of DEF. Take note, moment of inertia is 2i. So that's x. So we have e times 2i, y double prime df is equal to 11.25 times x plus 130.625 times quantity x minus 5, then minus 15 times x over 2, so minus 7.5 x squared. So we divide everything by 2 to simplify. So ei y double prime df is equal to 5.625x plus 1 plus 1045 over 16x minus 5 minus 3.75 x squared. Integrating once, so ei y df is y prime df is equal to 45 over 16 x squared plus 1045 over 32 quantity x minus 5 squared minus 1.25 x cubed plus c sub 5. C sub 5 is geometrically interpreted as the slope just to the right of D, this one. While C sub 6 would be the deflection at D, that one. So ei y df is equal to 15 over 16 x cubed plus 1045 over 96 quantity x minus 5 cubed minus 5 over 16 x to the fourth plus c sub 5 x plus c sub 6. Now, because there are two boundary conditions for portion DEF, we can solve c sub 5 and c sub 6 by two simultaneous equations. First, we set x is 5 for portion DEF, y is 0 into this equation. So 0 equals 15 over 16, 5 cubed. So this is 0 minus 5 over 16, 5 to the fourth, plus c sub 5 times 5 plus c sub 6. So the second equation is 5c sub 5 plus c sub 6 is equal to 5 over 16, 5 to the fourth, minus 15 over 16, 5 cubed, and that is 6 to 5 over 8. So call that equation 2. Then when x is 11 in df, y is 0. So 0 equals 15 over 16, 11 cubed, plus 1045 over 96, 6 cubed, 11 minus 5 is 6, then minus 5 over 16 times 11 to the fourth, plus c sub 5 times 11, plus c sub 6. So simplifying this equation, 11 c sub 5 plus c sub 6 equals 5 over 16, 11 to the fourth, minus 15 over 16, 11 cubed, minus 1045 over 96, 6 cubed, and that is 11 c sub 5 plus c sub 6 is equal to 976.25. Call that equation 3. So solving equations 2 and 3 simultaneously by eliminating c sub 6, you may subtract equation 2 from equation 3 and vice versa. So we can now compute c sub 5 and c sub 6. So c sub 5, which is the slope just to the right of b, is 2395 over 16, while c sub 6 is negative 10,725 over 16, which is the deflection at D. Divided by ei, c sub 5 divided by ei would be the slope just to the right of D. So theta D just to the right is 149.688 over ei. Again, c sub 5 is theta at D just to the right. You just express this in decimal form. That's the decimal equivalent. While c sub 6 in decimal is negative 10,725 over 16 in decimal. So delta D is equal to negative 670.312 over ei. Having found the deflection at D when x is 0, for BCD when x is 7, then the deflection at D can be found, which is equal to negative 10,725 over 16. So we substitute it into EIYBD. because we need one more equation here, and set x is 7 for BD here, and YBD is equal to negative 10,725 or 16 over EI. So EI times negative 10,725 or 16 EI is equal to 14.375 times 4 cubed plus 5 over 6 times 4 to the fourth plus 45 times 7 square. Sorry, it's 2 square. 7 minus 5 is 2. Minus 2.57 cubed minus 5 over 6, 7 to the fourth, plus c sub 3 times 7 plus c sub 4. So that's the equation. So simplifying and establishing the fourth equation, 7c sub 3 plus c sub 4 is equal to, so manipulating these constants, simplifying using your calculator, and that is 3995 over 16. We then solve equations 1 and 4 simultaneously by eliminating c sub 4 for convenience. So we get these three constants. Again, c sub 3 is the slope just to the right of B when x is 0 for BD, while c sub 4 is the deflection at B. So solving equations 1 and 4 simultaneously, c sub 3 is 1185 over 64, while c sub 4 is negative 26865 over 64. So therefore, delta B, express this c sub 4 in decimal, that's the deflection at B. So negative 26865 over 64 in decimal is negative 419.766 over EI. Having found delta B, we can now solve theta D that's to the left into this equation here, because we already have c sub 3, and we set x is 7 for BD. So into this equation, x is 7, so EI theta D just to the left is 43.125 4 square plus 10 thirds 4 cube plus 90 times 2 minus 7.57 square minus 10 thirds 7 cube plus c sub 3, which is 11835 over 64. So computing this value using your calculator, then expressed in decimal form, we now have theta D just to the left, and it is equal to negative 242.578 over EI. So that's it for this problem. And remember, this is the last example on beam deflection by double integration method.